we have other stuff to get to. Hi, good to see you, everyone. Cool. Today, I'm going to talk to. This is a new lecture. This lecture didn't exist last year because there was actually no method that actually worked last year. But now we are getting there. It's very exciting. So this lecture is about scene representation learning without camera poses. Very exciting. Okay, so this is actually, I've directly lifted this from talks I've been giving recently. So now you're just seeing a part of my talk again. But I think it's actually good to remotivate where we are right now, okay? So just to be clear, what is our goal, right? We've been doing all of this stuff to train AI to infer 3D representations from images. That's our goal. And when we say 3D representations, the thing that we mean is like the kind of thing that you have in your head when you look around, right? Like you have this 3D representation that tells you everything about the scene that you're in. And of course, the question is from what data, and we've already discussed this. The only kind of data source that we have currently that is scalable is like video. So for instance, this is this Epic Kitchens data set, but there's of course many other natural video data sets, and that's the data source that we want to learn from. Now, if you think about video, right, this is something that is worth refreshing, is the key signal for learning from video is basically this idea of predicting the future, or alternatively like reconstructing the video, right? Like what is a learning signal that you can use? And we discuss this learning signal in the form of like autoencoding, for instance, right? We say, take a video, reconstruct a 3D scene. All right, so let's be specific. So for instance, what is the generative process of video, right? So for instance, how is this video generated? Video is basically composed of 3 parts, approximately. One is 3D geometry and appearance, like the 3D geometry of the scene and the materials. The other one is the ego motion in the scene, right? How the camera moves. Like if you look at this video, most of the variance is explained by the camera moving. The scene is most of the scene is static, right? Most of the variance is explained by the camera moving. By which I mean that if you only knew the 3D geometry and appearance of the static parts of the scene, and you only knew the motion of the camera, you could that is like 90% of what's happening in this video, for instance, right? Or in most videos, in fact. And then there's this final part, which is basically 3D motion and deformation. So like the scene is moving in this case as well, and that of course like is added complexity. But for now, we have been completely ignoring this, and we'll be ignoring it for a little bit longer until we talk about dynamic 3D reconstruction, which we will get to. So far we've been like focusing on this kind of video, which is basically this video where we say the scene is static and the camera is moving. And so far we've been assuming that, and yeah, just again, think about like what is the generative process of this video? How are these videos generated? In this case, the video is almost completely explained by 3D geometry and appearance plus only the camera motion, right? That's almost everything that's happening in this video. And I'm saying almost everything because that does not explain literally everything, right? So for instance, you can see these reflections on the ground. That is something that is not explained by the 3D geometry and appearance and the camera motion. Well, because for that you need to consider light transport and reflections, which, and that's why this is not an equal sign, but it's like an approximately. Like almost the video is almost perfectly explained by the 3D geometry and appearance plus the camera motion in the scene. So these are the kinds of scenes that we've been thinking about so far. And so far, we've been assuming that these camera motion, the camera is given, right? Just a brief recap of what we've been talking about so far. And in this case, we talked about this framework of differentiable rendering. And in this case, when the cameras are given, you can reconstruct the scene via this differentiable rendering framework. Parameterize your scene via some 3D scene representation. You have a differentiable renderer. You fit the scene to the differential renderer. Great. And then we looked at like things like NeRF, Planoxels. We discussed like a few different ways of parameterizing 3D scenes. We discussed a few different differential renderers, great. And we got these high quality reconstructions. Now the question we've kept asking ourselves, is this going to take us to where we want to go? Is this going to take us to our goal of like training these models that can go from images to 3D representations that are on par with human 3D representations? That's kind of the thing where we want to get, right? And the answer, of course, so far has been no. Oh yeah, I should remove this title vision foundation models, but you know, this word foundation model is really fancy right now. I actually hate that I use it because, you know, maybe some of you, like, you read this paper and you really, it's like, but it's just a very good term. So people call these models foundation models, like something that just kind of solves most of the problems in a problem domain. So I'm going to also call it that. So, okay, is this a candidate for the kind of model that we want to use? And the answer so far has been like, no. Why is this not a candidate? it's not scalable. Like we can't just reconstruct all the videos in the planet using this method. And there's a few reasons for that. One, it's like ultra expensive. It's like offline. And another one is that these representations require lots of image observations of some 3D scene, right? And we've already discussed that most of the time you don't have that many 3D, observations. So in fact, all of these scenes are captured, all of these scenes that are reconstructed photorealistically that you've seen on the internet and so on, these are always captured in a very unnatural way. Like literally someone, have you seen what these camera trajectories look like that these kinds of scenes are captured with, or these kinds of data sets? Great, no. Yeah, kind of. Yeah, so like the way it looks like is like someone, they literally take a DSLR camera and then they switch it to like, not video, they don't take videos, they take like lots, like single pictures, and then they take the camera and they do this like click, 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 and then just they collect like 1,000 images, and then you get something like that. Okay, and so that's obviously very far away from how you capture scenes, which is like I'm walking around. I do collect like a lot of observations of the scene, but I don't move around like that. Right, it's like, okay, so that doesn't quite cut it. So not really scalable. So it's not great. So so then we've been discussing this other framework, right? This framework of amortized 3D reconstruction, which is just generalizable 3D reconstruction, which means that now we are in this domain where we might have incomplete observations of the scene, like I don't know, like we have 4 images or 1 image. Then we have this neural network that takes the images as input, and then it outputs the 3D representation. And then we can build a differential render on top, and then we can train a neural network to do the reconstruction for us, right? And that's what we've been discussing for the last few lectures, right? We discussed PixelNerve, or like these, you know, local conditioning, global conditioning, like scene representation transformers, light fields, all of these things. Any questions on these topics, by the way? Anything that popped up over the last few lectures? Great. Good. And then, like, just for and now, again, I can ask you, like, is this now going to be the model that we can just, like, train at scale and it's going to solve our problem? Unfortunately, the answer, again, is no. And now, why is that? The camera poses. The camera poses are a bummer. Because, unfortunately, videos on the internet don't have camera poses. It's just videos on the internet. And we discussed different ways of getting camera poses, and we're going to go through these again, but this is actually a major limitation. Let's talk about the different approaches for getting camera poses. Some of them we discussed before, and some of them we're going to discuss today in the lecture. One approach of getting camera poses you already know. This is structure for motion in SLAM. So we said if you want to get camera poses, what do? Take a video, stuff into CORMAP, click go. Gives you camera poses and like a rough point cloud. And in fact, as we have discussed several times before, this is really how all of these methods work. Like literally each of these videos that you've seen so far first goes through a stage of bundle adjustment through CORMAP or some other bundle adjustment software. And some of these methods even rely on an initialization of their 3D geometry that comes from bundle adjustment, right? Like, for instance, the Gaussian splatting we discussed. Gaussian splatting relied on the sparse point cloud. By the way, did you ask your advisor?
Yeah.
What did he say?
That like he didn't think that this approach would be rendering that we created.
Oh, great. So like basically his advisor, Hans-Peter Pfister, right? Yeah, like he was one of the authors of this method of like doing Gaussian splatting back in the day. And so I thought it was funny that when I heard that he's your advisor, so he's at Harvard, so you can say hi to him. So like, cool. So yeah, so basically that's structure for motion. There's also methods that are called SLAM, and these would be worth talking about, but we are not going to talk about them. They would be worth talking about though, but it's kind of like a rabbit hole. But long story short, there's these other methods that are called SLAM. Like the most commonly used one is ORB-SLAM. So if you have any friends that are working in robotics or you work in robotics yourself, what they do when they want camera poses, they always use ORB-SLAM, which is basically like, are you guys using ORB-SLAM? Are you guys using ORB-SLAM? Yeah. Okay, how well does it work? Aha. Good. Ah, great, fantastic. This is really important. This is great. So some real-world experience. It works most of the time, is exactly the problem. So how many times have you entered a room and failed to figure out where you were. Not that often, right? Like usually you're pretty good at that. Like usually I'm pretty good, unless you're like drunk or something, right? So, but usually you're pretty good at like figuring out where you are in space. So it's actually kind of concerning that we've been working on this stuff for 40 years and like we still have these algorithms that fail. Okay, so we're going to talk about in a moment what the limitations of these methods are, but I think you can already kind of figure it out. Now we're going to talk about one other method that is actually easily discussed, that has recently popped up, which you might have even considered yourself. And there is this other way of estimating camera poses, which is this idea of taking the methods that we have seen so far for differentiable rendering and just asking, can we use those exact same methods to solve not only for the 3D scene, but also solve for the camera poses. So instead of assuming that we have the camera poses, let's just take a set of images of some 3D scene, and then in the same differentiable rendering framework that we've discussed so far, can we just also solve for the camera poses instead of just solving for the 3D scene? Okay, and examples for this are papers like iNerf from MIT, BARF from MIT, Mellon, this is a recent paper from Stanford. There's few other ones, NERF minus, it's like a rather, there's a few papers in this. Okay, so how do these methods work? Okay, so the idea is really, really simple. You might have considered it yourself before. So remember, this was the framework that we discussed so far, where we just assume that the camera poses are given. So reminder, you have videos, right? For every frame of the video, or you have a collection of images. For each of the images, you have a camera pose. That's the assumption. So now the idea of these papers is to say, assume we don't have the camera pose. What we're going to do is we're going to randomly initialize a camera pose for each of the images. And then we're just going to backpropagate into those camera poses as well during the reconstruction process. So just to give you an idea of how that works, right? You have all implemented this differential renderer already, right, in your homework? Yeah. Okay, so actually you could easily do this. Like the way it works is you literally, in PyTorch, it turns out that the code that you wrote is already differentiable with respect to the camera pose. There's actually nothing you have to do. And it's like, that's not an interesting fact. It's literally, you could just, if you have an image, you can literally take the derivative of every pixel with respect to the camera pose. It's like nothing special. So now all you do is you say, okay, I randomly initialize my camera poses, and I'm going to just have minimize the loss, and then I hope that like my optimization algorithm kind of like wiggles the poses into the right positions. Right? Does that make sense? So intuitively, very easy. What are some problems that we anticipate? So maybe someone has a guess. What would you anticipate? Would this work? Would this not work? Yes. Non-convex optimization. Yeah. Yeah. Big problem. So let's see. So like, let's say, for instance, you're doing this in a NERF framework, right? Which is how these papers first did it. So imagine that your scene representation here is a NERF, which basically is like, so a neural field, right? It's like a neural field. And if you want the neural field to have, like, if you want the neural field to be able to parameterize high frequency detail, like it has to look photorealistic, then we already know that just using a ReLU neural network doesn't cut it, right? So we talked about these other kinds of neural networks, for instance, Siren, where you replace the ReLU nonlinearities with the sign nonlinearity, right? And we remember the problem is if you parameterize a 3D scene via ReLU MLP, you get these like super blurry reconstructions. So you get like blurry images, you get like blurry side distance functions, whatever the function is you want to parameterize, you can't do it crisply. And then Siren, for instance, was the point, like, look, if you replace it with a sign nonlinearity, it can parameterize this high frequency detail. And then NERF does something similar, right? NERF does this positional encoding, the sine cosine embedding, right? You take you take the XYZ coordinates of your of the point that you want to decode, and then for each of the XYZ coordinates, you compute the sine and the cosine with like different frequencies, and that's the input to your neural network, just as a refresher. Okay, and now what BARF just does is what BARF in particular just does is exactly what we just discussed. So now they just take this NERF, they take this neural field that they parameterize via this neural field with positional encoding. They randomly initialize a camera pose for each of the images. They render each of the images with this random camera pose from this randomly initialized NERF, They get an image, they compare it to the ground truth image, they compute the loss, they backpropagate it both into the NeRF and into the scene. And now, as the key insight of BARF was, that is exactly this problem of local minima. But we actually already saw some ideas for escaping. Well, okay, so like, let's first talk about like one thing that you might consider happening. Imagine that your 3D scene was like was kind of just a lot of blobs, and it was kind of like nice and blobby, and there was no high frequency detail. Right, so imagine, for instance, your 3D scene would just be like like big Gaussian blobs that are floating in space. In that case, you would expect that this optimization problem that we just discussed would be somewhat easier. Like, and it might even work, right? Like, if you have like a few cameras that are observing this like scene where there's like just lots of these like blobs which are like colored, you might expect that if you compare the ground truth image to the rendered image, then you get like a reasonable gradient for like moving the camera to the correct location. And just as a reminder, we had this problem a few times before, like this problem of local minima when you compare images to each other, right? Who remembers the ball example? Ball on the plane? Raise of hands, otherwise I'm going to talk about it again. Okay, not everyone, I'm going to talk about it again. So the example was like this. We said, imagine you had a situation like this, where you had a ground truth image of a scene where we have like a colored ball that is sitting on a plane, and now you have some kind of like differentiable renderer of like your scene, and what you want to do is you want to solve for the position of this ball. So imagine that you had like some way of going from like a single variable, which is like x, which is like, let's say, the position of the ball, to this image. So it's like it's a differentiable one. Okay. So you parameterize this image in terms of just the position of this ball along this plane. Now we asked this question back then. If you compared these two images to each other, just in pixel space, so you took this pixel and you took this pixel, you compared their distance, you computed the loss, and now you backpropagate it through this image, you compute the loss, you backpropagate it into this location. So you take like, so this is the loss. So you literally take the derivative of the loss with respect to the position of this ball, and you try to optimize the position of this ball such that it fits the other image. That was the ball example. And we discussed what would happen. If you did that, what would happen? Nothing, right? Because nothing happens, and why is that? It's because the two balls initially have no overlap. So if you wiggle one of them, like if you wiggle one of them around, the loss doesn't change, which means there's no gradient to push it into the right location. And then we discussed a way of fixing that problem. What was the way of fixing that problem? Yeah. Correct. So the way that we discussed this was we said, okay, we can blur this image. So we can take this image and we can just apply, for instance, a large Gaussian blur kernel. And what that basically does is it like makes this image blurry. And when the image gets blurry, then suddenly you have the situation that like, I can't draw Gaussians very well, but like imagine these were the level sets of the Gaussian, right? Now there is like, now if you move this Gaussian in the correct location, then the loss decreases. And now suddenly there's a gradient. And so you can imagine if you had a 3D scene that was like really blobby and kind of really blurry, then maybe this optimization problem that we're solving where we backpropagate into the camera pose has exactly the same property. Like, in fact, you can even imagine that, in fact, you can imagine it even in this case. Literally imagine that there's a 3D scene that you're looking at, and there's a ball sitting on the 3D scene, right? And now you have like one ground truth camera pose that looks at the scene, and you have a different camera pose that you initialize, which is just translated with respect to the correct camera pose. Then you would get exactly these two images, right? Like literally you are observing the scene from some ground truth camera pose in this case, and then you move the camera just left, and then you get this image, right? And now you're trying to backpropagate into the camera pose to make these two images fit. It's exactly the same problem, right? Then you have exactly the same problem again. Like if you try to solve it, it doesn't work. But if you blur it, then it suddenly works. Make sense? Great. And so, yes? Yeah, we're getting there. Good point. But so far, I just want to explain the key insight of BARF, this paper. Okay, BARF, bundle adjusting single radiance fields. So they basically said, okay, this is like this kind of stuff, local minima is like a well-known problem. And when you're trying to solve the optimization problem that we're just talking about, you will inherently face the same problem. Like if you And the way they explain it is imagine you want to align these two signals here. So you have two functions, f1x and f2x, and imagine it's actually the same function, but one of them is just shifted by some constant factor, right? So here the blue function is just shifted relative to the orange function a little bit. And imagine these two functions are really high frequency, and now you're trying to solve for the shift. So you're asking, you compute a loss between the two functions, which is just the mean squared error between the two functions, pointwise evaluated. And now you say, okay, I want to solve for the shift of function 1 relative to function 2. If the functions are high frequency, then that's not happening, because you fall into, similar to the thing that we just discussed before, you just fall into these local minima, where like, if you shift them, the loss looks like that. Like it's not a convex loss. So similar to our problem here, one way to fix that is just to make the signals smooth. So for instance, if you just smooth the two signals out, you just like blur them, for instance, then you get something that might look like that, and suddenly you have a convex loss, right? Suddenly, if you just if you compare the two functions and you just backpropagate into the shift, then you get a convex loss and you can solve for it. Does that make sense? Great. And let's think for a moment what would be actually the equivalent in this case. The equivalent in this case would be that maybe we have the two balls, and the two balls have overlap, but they have like a stripe pattern. So like you have like the two balls and they're striped. And now you have exactly the same problem, right? Like even though they are overlapping, when you shift them against each other, the loss like goes up and down and up and down and up and down whenever these two stripes overlap, right? And again, the same solution would apply. You could blur it, and then you would blur out the stripe pattern. And if your blur kernel is big enough, it would get convex again. You could solve it again via backpropagation. Okay, that was the core idea of BARF. And so what BARF does intuitively is exactly that. So here's an example of a toy problem in the BARF paper. They say, okay, let's assume we have this image of this cute little cat. It's a very cute cat. And now they're saying, okay, let's set up a toy problem to study this problem. And the toy problem they're setting up is they're saying, imagine we have cutouts of like, we assume that we have cutouts of this cat. So we have each of these little rectangles there is basically one image observation of the cat that we have. And then they say what we want to do is we assume we have these images, and given these images, we want to reconstruct the full image. And the thing we're solving for is one, the whole image, and the second thing is the position and the shape of each of the cutouts. So let me repeat that. Imagine what I would give you is I would give you the content of each of these rectangles, and then I ask you like a puzzle. I ask you to basically fit them together. So you want to solve for their relative position to each other, and you want to solve at the same time for the whole image. So this is actually exactly the same problem as the inverse rendering problem, right? I basically give you images, and you're now you're solving for the 3D poses, but fundamentally it's the same problem. You at the same time have to puzzle together the 3D scene out of these images that have some overlap in 3D, and you're at the same time solving for the camera poses as well as for the 3D scene, right? And what they found is if you now solve this problem exactly like naively, so you just parameterize this via like the same neural field that NeRF is parameterized with, so that has high frequency components via the positional encoding, or imagine you parameterize this via NeRF, via Siren, and now you're just naively doing this with backpropagation, so you at the same time backpropagate into the position of each of these cutouts as well as into the image, then you get this. Basically what's happening, right, is that the image, imagine you're initializing this like orange patch at the wrong location, like it's at the wrong location. And the orange patch, right, the orange patch contains the eyes of the cat. So what's going to happen is you will start your optimization process, and the orange patch is first going to start by like updating the image that is stored in the neural field. So it's going to generate a gradient that says, okay, I have these eyes of the eyes of the cat. So wherever I am initialized, I'm just going to try to make these eyes. So it's going to make these eyes. Now the problem that happens is that each of the patches does that. And so each of the patches starts generating high frequency detail before they are even approximately in the right locations. And then the final reconstruction you get looks something like that. And so what happens is that like each of the patches is initialized at the wrong position, and you get these local minima, and then the cat looks like that. Does that kind of intuitively make sense? Question? Yes? the problem is completely unsolvable if the pictures don't have any overlap. Yeah. Okay, so now knowing what we know now, what could we fix? How could we fix this problem? Blur. Yeah. Okay, so here's and now there's something funny, right? So like one way of blurring this thing is you could of course think about blurring the patches, fair. But you could also say, like, look, we can also pick a representation such that the representation maybe can't even generate high frequency details. So you basically say the image itself, we're going to make the image itself blurry. So we're not going to allow the image to have high frequency detail in the first place. So the way they do it in BARF is what you're seeing here. Maybe you can guess what it is. They just use this is a ReLU neural network. So if you try to solve the same problem with a ReLU neural network, where we know that the reconstructions always end up being blurry because the network can't even parameterize high frequency detail, then note that the optimization problem. I forgot to show the ground truth, but note that these are actually very close to the ground truth patches, and you can see that the cat looks actually pretty reasonable. Like the outline of the cat looks pretty reasonable. The patches also look reasonable, but now of course the reconstruction is garbage. And then, what does BARF do? BARF just says, okay, we're going to get the best of both worlds. We're going to start out by having a low frequency representation, and then we're going to schedule more and more high frequency detail over time. And the way they do that is they say, if you remember the positional encoding, the positional encoding had like frequencies that increased, had increasing frequencies. So it always did like sine, cosine embedding of each of the separate things, and then it increased the frequencies. How to say? Right. The position encoding looks something like this. You have an x coordinate, and then the positional encoding takes the x coordinate to like sine of x, cosine of x, and then it adds octaves. It says, okay, so that's the first one. Then we do sine of 2x, cosine of 2x, right? And then it says, okay, sine of 4x, cosine of 4x, and so on and so forth. So you basically you have several frequencies. And so all they did in this paper here is they say, okay, we start out by setting all of these high frequencies to 0. So we start out with basically like only having the low frequency embedding of the coordinates. And then you can imagine it acts a little bit more like a ReLU neural network. We discussed that what this positional encoding does is it basically acts like a Gaussian kernel, right? So that basically means it's like a Gaussian that is really blurry. And so initially it's all very blurry, and then it would converge to the correct locations, but the image is blurry. And then over time, they basically make the other components non-zero. So they start out with only the low frequency components, then they add high frequency component, and so you basically start out with blurring, and then it kind of shifts into the right location, and then it gets sharp. Does that make sense? Great. And now, do we foresee any problems with this? So I mean, Cairo already gave it away. Yeah. So this is a neat idea, and this paper is fairly well cited. But unfortunately, it doesn't actually work. And the reason why it doesn't actually reliably work is because even if you do all of this blurring shenanigans, there still are a lot of local minima in this optimization problem. So imagine, for instance, there would be two cats in the scene, right? Like two cats like this one, and they would be like next to each other, for instance, right? What will, even if you blur it, what will happen is that imagine one of the patches that is actually seeing cat number 1 gets initialized at a position that is closer to cat number 2, and it'll just get stuck there. And what does it mean to get stuck, right? Like the image is going to start forming, and the image is going to start forming with like two blurry cats, and one of the patches is at the wrong location. And now, what it means to be in a local minimum, right, is it means there's no, if this patch would go to the correct location, on the way the loss would increase. If there's no path for the patch to go from the wrong location to the good location, where the loss is monotonically decreasing, it will never get out of this local minimum. And that's exactly what happens. And this is exactly what happens in the 3D scene as well. Basically, because there's like lots of, and in the 3D scene, you can imagine that it's even worse. Imagine you have lots of images of this bottle, right? And now you're doing the same trick. You're saying, okay, we have like lots of images of this bottle. we're going to randomly initialize our camera poses around this bottle. And now we're backpropagating both into the NeRF and into the camera poses. Because this bottle looks basically the same from all of the different angles, if a camera pose starts out here, but should actually be on the other side, what will happen is it'll wiggle a little bit, and then it'll never move again. Because there's no way for it to, like, it would have to move all the way around to get to the correct thing, and that will never happen. And so in practice, this doesn't work. Like, it doesn't work strictly in the sense that if you start with randomly initialized cameras, it will not give you the correct camera poses after the optimization. But do you think it's still useful for something? And what could it be useful for anyways? Yeah. Huh? Maybe. Not what I'm looking for, but maybe. Photo stitching, right? So yeah, maybe this question is like not a very good question. The thing that it's still useful for is, imagine your camera poses are already almost correct. You're already almost correct, but now what you're asking for is you want to get these last, like, it's like just not literally exactly correct. And this last tiny bit of optimization, that's where this framework can get you really far. And it turns out, in fact, today, the best way of getting camera poses, like actually perfectly precise camera poses, looks exactly like that. What you do is you take a bunch of, like, imagine we have this in my research group right now. We have like a robot, and we have a bunch of cameras around the robot. So now you want to calibrate the camera positions. You want to know exactly what the camera poses are. What you do is you take a bunch of images and you throw it into COMAP, step number one. Okay, and then COMAP gives you like pretty good camera poses. They're like actually quite good. But even COMAP, turns out, will not give you this like last tiny bit of correction. And then actually what you do is you reconstruct a NeRF, or like one of these like scenes from the camera images with the COMAP initialization, and then you do this tiny little bit of like optimization, which then wiggles the camera poses just into the right position. And that turns out gives you like just the last tiny bit of calibration. And this is actually really funny because like this is something that has, this is like not, a major advance, but it is interesting that like these differential rendering techniques that we have been discussing, this is where they show up in the real world today. In real world applications, is if you actually want perfect camera poses for like solid, like mounted cameras, this is the way to go. Okay, great. Good, okay, but unfortunately, this doesn't actually solve our problem. So like, in other words, if I take a video and I try this, doesn't work. Well, unless sometimes you get lucky, or if the scene is very simple, you get lucky, but it doesn't actually get us there. So, so that's this joint NeRF and pose optimization. And as you can tell from the amount of time we spend on this, it's like, the basic concept is simple. Like really the way to do it, like all of you can do this. You just reconstruct the NeRF, and then you just say, okay, now also backpropagate into the poses, and it just goes. Okay, good. Now we already discussed one other way of doing pose estimation, which was the lecture number 4. We talked about self-supervised monocular depth estimation and pose estimation. Do you guys remember how that worked? Brief reminder. So the input was basically we have these videos, and now given a large data set of video, we want to train a neural network that learns to predict both the camera poses as well as the monocular depth for each frame. How did it work? It worked like this. We basically made one convolutional neural network, or like vision transformer, doesn't matter, that takes an image as input and maps it to a depth. And then we built another neural network that took 2 consecutive frames as input and output the camera pose. Remember? And then what did we do? We used as a loss this kind of warping loss, right? So like, I mean, this image is not very informative, but I hope you remember it. The way we supervised it in a self-supervised way, so we didn't require ground truth poses or ground truth depth. The way we supervised it is we used the predicted poses and the predicted depth to warp the consecutive frames onto each other, and then we just had a reconstruction loss on the image space. Do you remember that? So we had, we had like this thing where we had frame at time t, frame at time t plus 1, frame at time t minus 1. We predicted the depth for, actually we only predicted the depth for the center one, so we predicted the depth for this one, depth, and then we had the pose between those two. We had the pulse between those two. We had the pulse between those two, and then we use this depth to basically say, I want an estimate of frame t, and the way I'm going to get it is I'm going to take this pulse here, and I'm going to use the depth and the pulse to warp frame t plus 1 onto frame t, and then I'm just going to enforce a reconstruction loss on frame t. Do you remember that? Questions on that? No? Good. Fantastic. And that kind of worked, but as we already discussed back then, it in practice doesn't reliably work for complex camera poses. So like it works for the self-driving scenes, as this video impressively showed us back then, right? So this was a video from one of these methods where after training time you can do this inference where you give it a video and then the video just gives you these the depth. And with the poses and the depth, you can then reconstruct this point cloud that we saw last time. But unfortunately, in practice, it really only works for self-driving video. It doesn't work for arbitrary video where someone is walking through the scene. And back then, I kind of teased it, but we didn't discuss why it doesn't work. So why does it not work for general real-world 3D scenes? And that's what we're going to discuss now. Or rather, we're going to discuss an alternative to all of these three approaches that actually works. How exciting. So again, in practice, this is really the only area of computer vision where the state-of-the-art approach, which is structure for motion or COMAP, doesn't use any deep learning at all. So like the state-of-the-art approach that people use doesn't use no deep learning in the pipeline. Okay, so here's a paper that my group wrote recently, which is called FlowCam, Generalizable Neural Scene Representations Without Camera Poses. And you might have heard a little bit about it from Ayush, but he told me he didn't talk too much about it, which is good, because now we're going to talk about it in detail. And now we have all the pieces that we need to understand this paper. And this paper is a little hard to understand, so we're going to talk about it in detail. So here you can see what FlowCam does at test time. So FlowCam takes a video of like some object as input. In this case, it's a fire hydrant. Exciting. And from this fire hydrant, you have a neural network that actually outputs the camera poses in real time. So this works at 20 frames per second. And it also turns out at the same time reconstructs a generalizable scene representation. So at the same time, it reconstructs a pixel nerve. So here you can see a pixel nerve that is reconstructed of the scene from the video. And you can see it like kind of like changing every so often. And that's because what this pixel nerve does is it always reconstructs the scene from like 5 frames or so in the video. So it always takes, in a sliding window way, it always takes like 5 frames of the video, and then it reconstructs the 3D scene from those 5 frames. And that's why it's not consistent over time. So it's always switching between the 5 frames. Okay, and so this actually kind of works. And now we're going to discuss the magic sauce. Why does it actually work? Okay, the input-output behavior is the same. So the input is a video. And so this is a trained method. So just to be clear, at training time, you'll have lots of videos. And it's a self-supervised method, so it only requires videos. It doesn't require anything else. Okay. So let's go through a forward pass. So in the forward pass, what we're going to do is we're going to take a series of consecutive frames as input. And our, just to give it away, our reconstruction object, our loss will be reconstructing that video. That will be the only loss that will be almost the only loss we're going to use. So the objective will be take this video as input, given the video, reconstruct both the nerve and the camera poses, then re-render the video and have a reconstruction loss on each of the frames. And then we train it end to end. Okay, and now here's kind of the, I'm first going to give you the intuition of the approach, and then we're going to talk about how we implement it. So the intuition kind of works like this. It was actually kind of motivated by asking ourselves, like, how might it work in the brain? No one knows how it works in the brain, but you do this constantly. When you walk through the world, your brain constantly estimates your camera, your ego motion from the video stream. And actually, all of you have had the following experience. If you sit in a train car, and you look out the window, and next to you there's another train that is standing, and that train starts moving, what happens? It feels like you're moving, right? Your brain is like, oh, I'm moving. And then it takes a moment for your brain to be like, wait, no, my acceleration sensors in my ears don't tell me I'm moving. I know what's happening, the other train car is moving. But for a brief moment, you have this feeling you're moving, which kind of is the hint that your brain is reconstructing ego motion from motion, right? Your brain observes motion, and that's the cue that it uses to reconstruct your own motion in space. Okay, so here's a guess at what might be happening. And this is like kind of loosely supported by some insights from neuroscience and cognitive science that we have on what might be happening in the brain. One thing that we think might be happening in the brain is that your brain might be computing optical flow, which we didn't talk about yet, unfortunately. But who knows what optical flow is? Okay, who doesn't know what optical flow is? I see. We need an undergraduate class in computer vision. We don't have one at MIT. So here, it's totally fair to not know what optical flow is. Actually, it's explained very easily. Imagine you have a video, right, just consecutive frames. Optical flow tells you for every pixel, where does that pixel move in the next time step. So it's a optical flow. Optical flow is looks like this. So you have frame t, you have frame t plus 1. And then optical flow is a 2D flow field. So for every pixel, it's like a little vector that tells you where did this pixel move in the next frame. So imagine that this pixel moved from here to here. Then the optical flow will be exactly a vector that points there. Does that make sense? We're not going to talk about how to get optical flow today. That's in the future. But let's just assume that is a thing. Okay. And so we think that this is actually something that your brain is doing all the time. So we think that all the time with your brain, note this is just in 2D, right? This is just a thing. In 2D, where did every pixel move? This doesn't have any 3D component just yet. This is just optical flow. And we think this is something that might be happening. So basically, imagine that constantly what your brain is doing when you're walking through space, your brain is constantly computing for every point in space, how did it move in 2D on your retina, basically. Does that make sense? Okay, good. So now another thing that we think your brain is doing is basically depth estimation. And actually, that's not like wild, right? Of course, you have stereo cameras. So of course, you have depth from stereo. But even just with a single eye, you have like monocular depth. But have you ever noticed? I mean, I would encourage you to do it right now, but it's going to be a little awkward if everyone starts walking around. But like, have you ever noticed when you walk around, you walk and like it feels fine. And then when you close one eye, the ego motion feels different. Like it actually feels different walking around with one eye versus walking around with both eyes open. It almost seems like it's harder to get your motion estimate, like your ego motion estimate. I think that's probably true. So another thing we think, or like we're actually certain your brain is doing is depth estimation. That's the point of stereo cameras in the first place. So now here's the funny thing. Imagine you have for every pixel in space a 2D motion, and for consecutive frames you have the depth. So for every consecutive frames, for every pixel now you have two things. You have how far is it away from the camera, and you have how did it move in 2D. Can you imagine that? Yeah? Let me draw it in 1D. So imagine you have, I should have kept this. So imagine you have consecutive frames that look like this. Maybe there's we really like this toy example with like a ball. So there's a ball. Imagine there's a ball like here. And then in the next frame, the ball is like here. Okay, so imagine that the way these two images are generated is that there's actually a ball in 3D, and then there's a camera, right? And here the ball is like on the left side of the image, so maybe the camera is like somewhere here. Right, so like this is the image plane, right? So this is how this image is generated. The camera is here, and it sees the ball from there, right? And now imagine from t to t plus 1, right? What did the optical flow do? The optical flow looks like this, right? So like this point got mapped to here, this point got mapped to here. Make sense? Okay, good. Now imagine we have the depth. So we have the depth for frame t, right? So at time step t, the camera was here, and the depth, still no other camera. So the depth was basically this, like this distance, right? For every pixel here, you have this distance to the camera origin. That's the depth. Remember what depth was? Yes, good. Okay, so for every pixel you have camera. Okay, so where was the camera for the next time step? So the ball is like further to the right. So the camera was further to the left, right? So let's draw that really quick. So here, maybe in the next time step, the camera was here. Close enough, right? So here now it's in the center, and again you have the depth for every pixel, right? Now something funny happens. What does the optical flow tell you? The optical flow tells you basically correspondence. It tells you for every pixel in frame t, where did it go in frame t plus 1? So what's the corresponding pixel in frame t plus 1? And what that actually means in practice is if you look at these 2D vectors, if you have a depth for each of these pixels, they actually tell you a 3D vector. They tell you a 3D vector, like in this, if you think about this frame, right? So the pixel here on the right-hand side of the ball is like here. So if you know that the flow pointed like that, you can actually, using the depth, get a flow vector that is in 3D. So you can basically take the 2D motions, and using the depth from frame t and t plus 1, you can lift them into 3D, to little 3D flow vectors. Questions? Does that make sense? We can talk about it a little bit more. It's like like there's other ways of explaining it. Let me explain it in one different way. Who remembers unprojection? Who remembers the unprojection operator? Okay, so the unprojection operator, what did it do? It took a depth as input, right, and a camera pulse, and using a depth and a camera pulse and a pixel coordinate, it gave you the 3D coordinate of that point in camera coordinates. Remember? Good. So now imagine you have 2 consecutive frames, and you have the depth for each consecutive frame. So you don't know the camera pulse. You have to assume the camera pulse's identity. You don't know the camera pulse. So okay. So now you can take each pixel and you can lift it into 3D using the unprojection operator, right? You have the identity pulse. You lift each pixel into 3D, so you have a 3D point cloud. But the trick is that these 2 point clouds, right now the camera is at identity and the scene moved, right? So it's basically like you're keeping the camera constant, but the scene moved. It's the same as if you keep the scene constant and the camera moves. And now all you have to do is you have to take the 2 point clouds and you have to ask, how can I align them? What is the motion that best aligns these 2 point clouds? And that's going to be exactly the camera motion. Good. So that's what we're doing. So let's talk about how that works in practice. So what we do is we take 2 consecutive frames of this video as input. We take these 2 consecutive frames, and the first thing we compute is optical flow. So here, this is what optical flow usually is visualized like. The color is basically the direction of the vector. And so like these different colors just mean different directions. But basically the optical flow is like a little vector, right? So for every point here, you basically get a corresponding point here. So in this case, the thing rotated, right? So in this case, you can see that this part of the fire hydrant is this part of the fire hydrant, and so the flow will point like something like that, right? So for every pixel, you have this correspondence. Now what we do is we take a generalizable null scene representation, pixel nerf in fact, and we take these 2 frames separately, and we reconstruct a nerf from each of these 2 frames separately. So basically take the single frame as input, we reconstruct a nerf using pixel nerf, and then what we do is we render the same nerf again from the same camera pulse. So the way you can think about this is like predicting the depth, right? You're basically reconstructing the scene from that single frame, then you're rendering it again, and using the renderer you get the depth, and you get of course the image again, but the image is irrelevant. So just imagine we predict the depth. So for each of these 2 frames, we basically predict the depth, and here we're visualizing this as a point cloud, right? So this is like monocular depth prediction. Take image as input, predict point cloud. And now, because we have these 2D correspondences, we basically now know that this 3D point here corresponds to this 3D point here. And that's the thing that gives you the 3D vector. So for every point in this thing, we get a 3D vector that tells you where did it move in this frame, just by virtue of looking at the optical flow and looking at the 2 point clouds, right? And this gives you this little flow field here. So now this is what it looks like. So for every point in the point cloud, you now get a 3D vector that tells you this is how it moved over time, as if the camera stayed constant but the scene moved. Okay, and now all you have to do, which we're not going to talk about how to do that, but it's not that complicated. All you have to do is you have to ask what is the what is the camera motion that best explains this flow field. So you're actually solving a little least squares problem. So you set up a little least squares problem. You say, okay, solve for a transformation that basically reproduces this motion. And you know it's just a single. What are we solving for, right? You're solving for just as a reminder, a camera pose looked like this, right? Rotation, translation, 1, 0. So this is what you're solving for, basically. You're basically saying, I have these 2 point clouds, and now give me the rotation and translation that best aligns these 2 point clouds. And that's formulated just as a least squares problem. And the way this is solved is called Procrustes. So there's different ways of solving this problem. One way of solving it is if you don't know which 2 points correspond to each other, this problem is ultra hard. If I just give you 2 random point clouds and I ask you to align them, and they're not identical point clouds that are just randomly oriented, then you're screwed. Like it's called ICP. It's like, I don't even know what ICP means. Does someone know what ICP refers to? Thank you. Iterative closest points. Like an iterative algorithm, it works 0% of the time if the 2 point clouds have any noise in them. Someone's nodding. Good. I'm exaggerating. It's a great algorithm, but it actually doesn't reliably work. So the reason why this thing is tractable is exactly because you know which 2 points belong to each other. So intuitively, it's actually really easy, right? Imagine I ask you, if I just give you 2 points, all you have to get is you have to just get the distance between the 2 points, right? If I give you a set, like if I give you 2 pairs of points, then you can imagine that you just have to minimize these points. Like if you know that, to draw it again. Like this is actually kind of funny. If you have these 2 pairs of points, and you know that this point corresponds to this point, and this point corresponds to this point. If you know that, all you have to do is you have to minimize the length of these 2 vectors. That turns out is a really easy problem. If you don't know that these points correspond to each other, the problem is ultra hard. I mean, not in this case, but like if you have more points, there's all these local minima. Like which way do you flip them, for instance, right? Even in this case, there would be 2 possible solutions, right? Like there's a symmetry here, so there's a local minimum. It's good. But if you know the correspondences, it turns out it's a really easy problem. So this is what this optimization problem looks like. So the way you would note it is, say you have point cloud x, which is from time step t. You have point cloud xt plus 1, which is the point cloud that you get from a consecutive frame. And then you say, I want to solve for the pose. So I take each point here, I transform it by the pose, and then I just minimize this loss. So you're just minimizing over the space of poses such that this is true. Okay, there's a little bit, so far so good. Any questions? Yes? Great question. So the question is, what happens with occlusion? So first of all, does the question make sense to everyone? What happens to occlusion? So why is occlusion the concern? In this toy example, actually even in this toy example, it's a problem. But of course, when you're moving the camera around something, or even if you move your head right now and you look at literally anything, you're disoccluding something and you're occluding another part. So basically, some pixels go away and some pixels pop up that don't have correspondences in the consecutive frames. David is an expert on this, actually. So David is working on optical flow right now, and this is kind of really annoying. So basically, there's pixels that don't have correspondences. And so what does optical flow do? If you use any optical flow algorithm, the optical flow algorithm will just give you garbage for these pixels. It'll just give you random. Usually it would give you, basically unreliable. At all the points that don't have correspondences is unreliable. And now, of course, this would be a problem, right? Because for each of these points, we will still lift them into 3D, and we still have, we still use this garbage correspondence to basically build this 3D motion, like this 3D motion field. And the way you deal with that is this magical W in here. So thanks for asking the question. So here there's this little W here, and maybe you can imagine what this W is. It's a W because it's a weight, and actually what you end up solving is a weighted least squares problem. So what you're going to do is you're going to say, instead of just, let's say we had a situation like this. No, I can't explain it with an image. Just imagine that some of the correspondences are garbage. All you would want to do is you would want to say, when you're solving the least squares problem, you're ignoring, you're setting all of the contributions of all of the correspondences that are bad to 0. Okay, but now how do you do that? And the intuition is very simple. All you actually do is you take the optical flow, and then you imagine you do the following. You take the color of this pixel, and you take the color of this pixel, you compare the two colors. If the two colors are the same, then the correspondence is good. If the colors are not the same, the correspondence is bad. Right? That seems like an easy heuristic. Of course, colors are not the most reliable thing. So actually what you do is you build a little neural network, this little neural network psi here, and F1 and F2, what are F1 and F2? F1 and F2 are the per pixel features, are like the pixel line features. So when you take this image, you put it through a convolutional neural network, you get a feature for every pixel, and you take the feature from this thing, and you take the feature from the other one, and then you give these two features to just a little fully connected neural network, and that's going to output a weight between 0 and 1. Okay, now what can this fully connected neural network do? It's very interesting. One thing it can do is it can compare the two colors, right? It can learn this very dumb thing, which is like if the two colors are not the same, the correspondence is not good. Okay, you can reject like quite a bit of shenanigans with that one. Another thing it can do, pop that on the stack for a moment because we're going to talk about the loss and then we're going to come back to the weights. Okay, so just for now, let's imagine we could magically conjure up for each of these like 3D flow vectors, we could magically conjure up a weight. And for all of the bad ones, it would be 0. For all of the good ones, it would be 1. So we reject all of the ones that are, for instance, occluded or that are just bad correspondences. So now we have a pose for this consecutive pair of frames. Now what we're going to do is we're going to get poses for each consecutive pair of frames. So we're just going to run this on each consecutive pair of frames. We get a pose for each pair. And now we can just basically put the poses in a row, right? And we can reconstruct all the poses for the whole video in that way. And then all you do is you take, for instance, the first frame and the last frame. You use the first frame and the last frame to reconstruct the nerf again with like a pixel nerf or one of these other generalizable nerfs that we talked about in the last 3 lectures. And then you can re-render this nerf from all of the camera poses. And that's going to be one loss. So you re-render every frame of the video using the camera poses and this nerf. That's loss number 1. And the second thing you do, turns out to be important, the second thing you do is you say, okay, when I take this 3D flow and I project it onto the image, that should give me optical flow. So basically, when you have the 3D flow vector and you project it, that should give you exactly back the optical flow. And that's the other thing you have a loss on. So you have a loss on the RGB images, and you have another loss on the optical flow that you computed. This is like a lot. Does this make sense? So before we talk about the weights more, does this make sense? Any questions? Yes? Great question. So the question is, why would this ever be fast? Because clearly, to get this point out here, you have to do reconstruction. Actually, to do all of these things. Okay. So the first thing is, if you want to do this for reconstruction, if you want to use this to get the poses, you don't care about the second part. Like everything that is in the box here is the thing that you need to compute the poses. The other stuff is just actually a training time if you want to render it. But you don't need to render it when you want to estimate the poses. For the poses, you just need the stuff that's in the box.
You could do self-rendering, right?
Yeah, you just need to render these. And that is, unfortunately, relatively expensive. But here's the second trick. The second trick is that these renderings don't have to be very high resolution. So this you can render at like really low resolutions, and because all like this problem here is actually fairly robust, right? Okay, how many points do you actually need to solve this optimization problem? It's actually technically exactly as many degrees of freedom as the pose has. And the pose has 3 degrees of freedom in the rotation and 3 degrees of freedom in the translation. So actually, to solve this little least squares problem, technically you only need 6 points. So now, of course, that if these 6 points are noisy, then it's going to get shabby, it's going to get bad. So if you have more points, the least squares problem is going to get better, as long as there's no outliers. But we're going to talk about the weights in a moment. So that's why. So you don't actually, I think in practice, we render these things at like a resolution of 32 squared. It's like 32 side length, and then that's really fast. Other questions? Great, okay, good. So let's talk about the weights. So just as the question was asked, like imagine the optical flow is like bad. For like some of the pixels, the optical flow is bad, either because there's occlusions or just because the optical flow algorithm did a bad job. So what we want is for every correspondence, we want to predict whether the correspondence is good or not. And the way we do it is the way I just discussed it. You take per pixel features that are in correspondence. So like you take this feature, you concatenate them, and you put them into a little neural network, and the little neural network is going to predict you for every pixel how confident am I in this correspondence. And now this is really something to think about a little bit more. So one thing we already discussed, it can just look if the colors are the same. If not, then it throws it out. Another thing it can do is it can do something that is more useful than color. So for instance, right, because these are neural network features, the feature can say, okay, yeah, this is the same color, but this feature here is actually the top right of the chair, and this other feature is the center of the chair, right? Because this is like a convolutional neural network, it can give you some higher level features, so it can reject those as well. So even if the color is the same, it can reject things according to like higher level features. But here's another really interesting thing it can do. It can reject things according to semantic class. It can, for instance, say, I'm never using correspondences that come from cars, because cars often move. Right? So like you can basically this little thing can look at the features in isolation. It can say, okay, this feature comes from a car. I don't like cars. Cars are bad. Don't use. Another thing it can do is it can do stuff like, okay, this feature comes from a microwave. I don't know, there's a kitchen, there's a microwave, and microwaves are often shiny. Shiny surfaces are no good for correspondence estimation either, because they are not multi-view, like specular highlights, like reflections are not multi-view consistent. We don't use these either. And this is in fact something we look at in the paper, and it is in fact true that this thing learns to ignore, like actually the number of points it uses is very sparse. It looks at the whole image, and I think it uses like 20% of the pixels, and everything else is just like, don't need that. Because technically it only needs 6 correspondences, so it can be very picky in which correspondences it uses. And yeah, notably, right, this is all end-to-end differentiable, so there's like no non-differentiable part in this. This is, yeah, I should point out this is also differentiable. And the reason why this is differentiable is actually just the normal equations. So remember the solutions to these squares problems, like linearly squares problems, right? You learned these normal equations. Do you remember that? Like, so the solution to this looks a little bit like that. The solution to this ends up being like inverse of that, pseudo-inverse of that, transpose that, and it's just a big matrix that you like multiply with the points. Yeah. Yeah. Yeah, absolutely. So the question is like, why would it ever learn to reject like motion and stuff like that? So the reason why is because it'll learn to reject anything that increases the loss, right? So imagine, but this is a subtle question, it's a very good question. So what would not work is if you had a video where like a large part of the scene was moving. Like imagine you're looking at like a street and there's like a car and the car is really close to the camera and it's driving past, or you're sitting in a train car and you're looking to your left and there's like a train car that is taking up a lot of your visual degree and now it's moving. So what happens in this case is that if you think about the least squares loss, like the re-rendering loss at the end, so what this thing is doing, right, it's reconstructing the poses and then it's re-rendering the scene from these poses. If a large part of the scene is moving, then the parts that are moving have the highest impact on the loss. So like the model is going to try to actually, in fact, in the example with the train car, just like what your brain is doing, in the example with your train car, like you would try to explain your ego motion using the motion of the train car because that's making up the most of your field. But imagine instead that the part of the scene that is moving is very small. Then most of the re-rendering loss is going to be dominated by the static background. And now what happens is if you include the optical flow from the thing that is moving in your pose estimation, then you're going to screw up all the background. Because if you're like, imagine you keep those in your like, right, let's think about how that would look like. Yeah, so like imagine magically the fire hydrant would be like shifting to the left, and the background would be like a lush forest, and the fire hydrant is moving is shifting, right? Then basically this flow field would have 2 components. One would be the motion of the high fire hydrant, that would be the thing that's moving, and then everything else would point in the other direction. So now if you used a least square solver to solve for the ego motion of that, to solve for a single pose, it'll be like an average of the motion of the fire hydrant and the motion of the background, right? Because the least square solver will get the thing that minimizes the total error. And then basically what ends up happening is that you get the wrong poses, and then you're going to mess up the rendering of the whole background. Because now you're going to re-render the nerf, and when you render it, it's going to look like garbage. And that's the signal for, and that's exactly the signal that you get for rejecting the moving part. So you basically say, okay, I want to do a good job at rendering the foreground because the background, because the background is the thing that makes up most of the image. And if I include this moving thing, it's going to mess it up. And that's the signal for it rejecting the moving parts.
Like things like motion or
yeah. So basically, exactly. So like you would basically mess up the pose estimation, and the pose estimation will lead to like rendering all the static parts of the scene poorly. And then that's why you're going to reject it. But if these kind of artifacts make up most of the image, then you're just screwed. Then there's like, in this case, there's nothing you can do because this loss is not going to give you a good signal in that case. So. Other questions?
are they generated by neural network trainable?
Yeah.
Why? So I'm the neural network. I'm always going to generate zero because that will always give you the loss equal to zero.
Which loss?
The loss of the
Here?
Yeah.
Ah.
Yeah. I will please make it zero. How to prevent the neural network fight from always generating zero?
Good question. So note that this optimization here is like, just for the record, right? Like first of all, this optimization here is not over W, right? So this least square solver is not solving for W. This least square solver is only solving for P. This least squares problem is like W is fixed. You give me a fixed set of weights, right? And then it's just solving for P. And your question would be correct if these square laws would be part of the final loss, then that would happen, right? If you took like, so maybe I should clarify this. The loss that we're actually supervising, the loss that we're minimizing in our, when we're training this model, only has these two parts. These are the ones that you're supervising. You're not actually minimizing this loss. You're just minimizing these two. This is just kind of like a differentiable block in your neural network. Does the question make sense? So the question was like, why wouldn't the neural network just learn to put W to 0? Because if W is 0, then this loss is 0. And that would in fact happen if you took this loss and added it to your total loss in the end, and then you minimized it, then that might happen. The neural network's like, great, I can set this to 0 by setting W to 0, but we're not actually supervising this loss. The only thing we're supervising is the re-rendering loss and the optical flow loss in the end. Good question. Other questions? Great. Okay, so here's some results. Here's like this fire hydrant, and like the fire hydrant is like we're moving the camera around, and you reconstruct this trajectory. Here's like this other object where and the reconstructed trajectory. So now, if you're a SLAM person, you know that these scenes are difficult because there's lots of rotation in the scene, and rotation, for reasons we're not getting into, SLAM algorithms don't like rotations. Here's another scene. So this is a scene from a data set called Tanks and Temples, which is like outdoor scenes. And actually, we just talked about BARF. So BARF, you remember what BARF did? This is the result that you get when you do BARF. So if you take all of these images and you just backpropagate into the poses and you're trying to reconstruct the nerf at the same time, this is the thing you're getting. It's just complete garbage because it constantly falls into local minima. This here is a model that we trained on real estate in K, which is an indoor data set, which is actually, as the name suggests, it's a data set that was collected by people running through commercial real estate. So this was a scraped data set. It's a data set that is scraped from the internet of like real estate videos of people like showing off real estate. So that's how this data set was collected. And we trained a model on that data set with the loss we just discussed. And without any fine tuning or anything, if you just do feed-forward inference, just like 20 frames per second, then this is the thing that you're getting. So you're getting a trajectory which is like kind of close enough, but not exactly. But then what you can do is you can take this video, and finally you can overfit on this video. So you can take the same loss that we just discussed, and you can just train a little bit on this video for like 5 minutes. You can just optimize the weights of the neural network specifically to minimize the loss on this video. And then the thing that you're getting is on the bottom right. So then you get almost perfect camera poses. And then we, this is not a nerve that is trained using those camera poses, but like this are, again, like these pixel nerves that are like from consecutive chunks of the video, and then this is the nerve. And you can see the depth is approximately correct, and the frames look reasonable. Okay, so now compared to SLAM, as earlier our student, what's your name actually, by the way? Peter. So Peter was previously like just laughing when I asked how often does SLAM work. The reason is because if you run it, even if you run it on these like toy videos, like stuff like that, if you run it on this data set, it fails like 50% of the time. I'm not even kidding. Like literally for casually captured video, if you run OrbSLAM v3, which is the state-of-the-art SLAM algorithm, which all the roboticists are using, run it on these videos, it fails literally 50% of the time. 50% of the time, it just gives you nothing. It doesn't even give you something. It just says like, sorry, no bueno. Okay, so we benchmarked with OrbSLAM v3 on these data sets here, and on OrbSLAM v3 fails 50% of the time. The method that we are proposing here is still not perfect, so this here is actually just the error. This is the pose error. So you can see it's a lot better than OrbSLAM v3, or another baseline is called DroidSLAM, which is actually really good, but don't have enough time to talk about it. We're significantly outperforming SLAM, which is cool, because SLAM people have been working on for 40 years. We have worked on this for half a year. So that's cool. Still, of course, far from perfect, right? Like, like this number should be 0. Like, just for the record, like COMAP, what is the error that you get when you run COMAP? The error that you get when you run COMAP is on the order of like, basically if you run COMAP again and again and again, and with random seeds, it should give you like variance on the order of 0.005 or like 0.003. So like 3e minus 3, which is like a lot smaller than this. But COMAP is offline, this is online, and we're getting there. Okay, so a few limitations. Actually, one thing I didn't mention is this still requires you to have camera intrinsics, so you still need to know the camera calibration, which is standard for SLAM. So SLAM always assumes that you have the camera intrinsic parameters. Structure for motion does solve for the camera intrinsics as well. So that's one thing we have to fix. Loop closures we're not going to talk about. It's clearly not photorealistic, whatever. Actually, the core limitation of this is that it still doesn't work on arbitrary video. It still doesn't work on video where people are moving. If like there's lots of motion in the scene, it still fails. And this is shared with structure for motion. If you remember, we talked about this. You literally cannot run structure for motion on scenes with motion in it. Which is kind of funny because it's called structure for motion. But what they mean when they say structure for motion is structure from camera motion. They don't mean structure from scene motion, because scene motion just doesn't work at all. So, getting there. And actually, Cameron was just visiting for 1 week. He's a visiting researcher, so this is Cameron, if you see him. Okay, good. So now this is kind of heavy. Now we're going to talk about like something that is much simpler for the last 12 minutes, which is a different way of doing this. But first, any questions on this, or no? Good. Okay. So here's another way of doing it. We already talked about like this thing called light field networks and light field transformers in the last lecture, where basically we said the motivation for this is that, okay, we can build all these 3D structured renderers, like volume rendering, but they're really expensive, and they can't capture all of the effects that we might be interested in. So for instance, if you have reflections, like these differentiable volume renderers can't deal with reflections, or if you have like scattering and stuff like that, it's difficult. Okay, so we talked about light field networks, where the idea was just, okay, instead of parameterizing a function that takes a 3D coordinate and maps it to a density and a color, instead we have a function that takes an array as input and just gives you the color of the array. And we said that doesn't work for overfitting at all, but it does work when you train it in a generalization framework, right? And specifically, I showed you these results from the scene representation transformer. Recall the way it worked is you take a set of images, you encode them with a CNN, then you stick them into a big vision transformer, big transformer. The transformer gives you a set of tokens, like this, what they call the set latent scene representation, but it's just a set of tokens. And then the way you do rendering is you take array, and then you do cross attention with that array over all of the tokens, and then that just gives you a color. Remember that on a high level, we don't have to recall the low level. So basically, and why is this interesting or cool? It's interesting and cool because there's no 3D structure at all in this, but then I showed you these videos, and clearly the transformer figures out how to do somewhat multi-view consistent rendering. So the transformer just figures out what 3D looks like by itself, and then afterwards you can render these novel views. Okay, so it turns out in this framework you can also train things without camera poses, and here's how it works. This is a paper from CVPR 2023. So was presented in summer this year at New Orleans, I think. Was it New Orleans? I don't know. So here's what you can do. We're going to take a set of input images. Note now they say unposed. So now we don't know the camera. Like previously, in the previous paper, you gave the transformer the camera poses as input as well. Now we don't give the transformer the camera poses as input anymore. We just give it the images. So we just say, here's a set of images. We don't tell you anything else about these images. Just go. Great. Question? Okay. Good. So you stick it into your transformer encoder, and the transformer is giving you a set of tokens. Okay, so now how can we proceed from here? What they propose to do is they propose to build a little pose estimator module, which basically says, so like how can I explain this problem? So at the end of the day, what do we want to do? At the end of the day, we want to render a target view such that we can supervise the target view, right? Basically, what does the training set look like? The training set looks like you have like 10 images of a scene. You want to give the transformer 9 of them, and then you want to render the 10th, and that's how you supervise it, right? The problem is for none of them you have poses. You don't have poses for the 9 input images. You also don't have the pose for the 10th target image. So how could you make this transformer do anything reasonable? And the way they do it is like as follows. So they take these 9 input images or so, they give you these tokens, and now they take the target view and they split it in half. And they say, okay, I'm going to give the transformer half of the target view. And then I'm going to have a little transformer that takes the tokens from the input views as well as the half the target view. And then I say that what that transformer does is it's going to estimate the pose between all of the input images and the target view. Imagine, like, just intuitively, this is not surprising, right? Imagine what you would do. I would give you a set of 10 images. What would you do, right? You would look at the 10 images, and then you'd be like, okay, so this image is kind of there, this image is kind of there, this image is kind of there, right? So the hope is that kind of this does the same thing. And then, given this half view, you then have a little, then you have another little transformer, and what it does is it completes the other half of the image. So the way you train this thing is you basically give it like some set of input images, you give it half of another image, and then you ask it, conditioned on both of these, figure out what the other half of the image looks like. Okay, why do you expect this to work? The reason why you expect this to work is, what does the transformer have to do to figure out what the other half of this image looks like? The hope is that it looks at half of the image, it uses that half of the image to figure out what the camera poses are between all of the images, and then once it has figured out the camera poses, it can reconstruct the 3D scene. Once it has reconstructed the 3D scene and the camera poses, it can then complete the other half of the image. So there's nothing to, so like if you don't understand it, you're not alone. No one understands this. Like it also doesn't work that well, I should say. So like it kind of works. Like I'm going to show you the video now. So it kind of works. So here's a video that you can get. So here's a video that you can render. This is called a data set called multi-shapenet. So you give it like an input, like a few input images of like these random objects that are dropped on like the ground. And here you can see the renderings, and you can see the renderings are pretty reasonable, right? Here, and they show like different novel views. So here they rotate the camera around the thing. Here they zoom in, and here they like just modulate the height of the thing. Yes.
I'm guessing at test time they're not giving target poses as well.
Great question. So the question is like, how do they control the camera? Because seemingly, like, what you can notice about this thing here is that there is no, like they say this. Okay, maybe I should talk more about this. So here they say latent pose. So like, how do they actually parameterize the pose? They don't actually produce like a like this rotation and translation matrix. Actually, they just produce like a little latent code. Like the thing just takes this thing and just gives you a little latent code, and then you take that little latent code, which they call the latent pose, and then they take that little latent code and they take the tokens from the input images, and then they give that to a transformer, they hit it again, and then it gives you the image. Huh? No, you never feed the other half of the input image to the decoder. So in fact, okay, so yeah, this is kind of funny. So so now the problem here is that there's a few problems with this, or like seemingly there's a few problems with this. One problem is you don't have a 3D scene here, right? Like again, this is like a light field, so there's no thing here you can sample at a 3D coordinate. It tells you what is at that 3D coordinate. The only thing that you have is you have a function, you can give it a ray, it gives you a color. That's what you have. So you can't get a point cloud from this easily, right? There's no way of asking at this 3D coordinate is something at that 3D coordinate. So that's a little bit bad. So there's no 3D structure. The other thing is that there's no actual camera pose here. So there's no actual camera pose. There's just this latent pose. And now the question that Kyra asked is, okay, sure enough, you can train this thing, but then after, like at test time, you give it a set of images, how can you move the camera? And the answer to that is they just wiggle around the latent code. So you just take this latent code, and then you basically, at training time, you get a bunch of latent codes, and then you just interpolate these training codes, and it turns out some directions in this latent space correspond to camera angles. In fact, I have a slide for this. In fact, here's what that looks like. So this is what this latent space looks like. So they basically say, at training time, they investigate this a little bit. So like they give the model like different kinds of images, and then they get the latent code, and then they do PCA on the latent space. So they basically generate lots of these latent codes, and then they do a principal component analysis, and then they ask, what does this latent space look like? And if you do that, you discover that the latent space, in this case, where the camera is always moving like up and down and around the thing, the latent space is exactly rotation plus the azimuth of the camera. And so this is how they do normal view synthesis. In fact, that's why I left this in here. Camera movement induced by traversal in latent pose space. So you just figure out here. Good. So so on this toy data set, it kind of works. Here's the real world data set. And if you look at the real world data set, it gets a little bit more adventurous. Like, I don't know. So like this thing here, that doesn't look amazing. So like, who knows what this thing does? It didn't actually exactly figure out the right thing, but like, you know, it's clearly showing signs of, I would say this is signs of life. It's not like working 100%, but it's signs of life. And why is this interesting, right? That's the reason why I'm telling you this. It's interesting because this is a completely different way of doing it. There was spent zero effort, like zero thinking about multi-view geometry. All of this fancy stuff we talked about in lecture 1 and 2, none of that thinking happened here, right? It's just build a big neural network, train it on a lot of data, and let it figure out its own stuff. And so that's why this is interesting. Okay, so summary. If I would have to make a guess, then my guess is that the landscape of camera pose estimation is going to look very different 2 years from now. I would guess, in fact, that in 2 years, no one in this room is going to use COMAP anymore. So we've been using COMAP since 2018. But structure for motion we've been using really for 25 years. So like around 2000, it started kind of working. Or 2005, 2006, it started really working. And there was like an insane amount of engineering effort. If you look at the code base of COMAP, it's written in C++, that it's optimized till infinity, has millions of lines of code, very complicated stuff, very impressive, works like impressively well. And yet, you know, with all of this engineering, it still only works like 90% of the time, and it takes forever. So that's not going to be the thing. And I think that right around now is the time where this is changing. And this is actually a very exciting time in computer vision for that reason, because just like deep learning revolutionized image classification and segmentation in 2012, right now deep learning is revolutionizing multi-view geometry and 3D reconstruction, which hasn't happened until now, but now it's happening. So consider yourself lucky. It's like exciting times. And I think this is my last slide. So if you have any more questions, feel free to ask them now. Otherwise, that's the end of the lecture. Yes? Maybe. Yeah. No. I think you're probably right. I would say there's like a 70% chance that that's what's going to happen. So there's a 70% chance that we're going to just train. However, I think the judgment on this is still out, so I don't know if we talked about this before, but all of you are probably using ChatGPT from time to time. What's your experience with ChatGPT? It works for 80% of the things, 80% of the time. That's my experience with ChatGPT. So like, for everything that is kind of close to things it has seen at training time, it works pretty reliably. Like, make this shorter, make this longer, like, I don't know, edit this and that, write this piece of code, all good. But try to make ChatGPT write a 2D